Okay, so this is section 5.3, page 285, the definite integral and antiderivatives. Today we actually are going to do calculus on the integrals rather than rely on geometry that we recognize the functions to be. But we're going to ease you into it a little bit. So one of the first things we're going to do is discuss that. We actually discussed it yesterday when we said if you've got, well, any area of a curve, I don't know, like this, and you're going to go find the area from here to here. It's all above the x-axis. If you integrate from a to b, used to writing function notation. If you integrate from a to b of f of x, will the answer be positive or negative?
Positive.
Positive. If you integrate from b to a, going backwards along the x-axis of f of x, what will you get?
Negative.
A negative, and here's why. Because you got to remember that these integrals are really just a collection of rectangles. So if I do this rectangle right here, that's one of the rectangles I'm going to collect. Then I will be using this for its base and probably the middle point for its height, something like that. And I will be integrating it right here in this direction. So all of my bases will be from a left piece to a right piece, and that's the length of it. I'll be going that way. The heights will be positive. If I'm integrating from b to a, then I'm taking all my rectangles coming back this way. And so this number from here to here will be a negative. It will be a negative base, if you will, times the height, and that will give you a negative value. Yes?
So if you were like it had negative x values and you were going b to a, would it make them positive?
Yep. So if I continued this thing down over here somewhere and I put a C over here, and I was looking at this rectangle, then if I'm integrating from a to c instead, here, and a or c to a here, if I'm integrating from a to c like this, I just changed gears. Let's go from c to a. On this one, c to a, that would be in the forward direction. And this would be a to c, that would be in the backwards direction. Then what I would have is, if I integrated from c to a, I would have positive values here and negative values there, would give me negative area, just like you said, okay? If I was integrating from a to c, then I would have negative values here, and this would actually turn out positive. Okay, so basically what we're saying here is this, folks. The integral from, and usually they use a and b, the integral from a to b is equal to the opposite of the integral from b to a. Changes the sign. Okay, that make sense? Yeah? Okay. That's the very, very first property or rules for definite integrals that you're seeing on page 285. And I want to go through each one of these, and most of them will make really good sense. The last two will make really good sense to you after I explain the crazy notation. So, order of integration. If you go from b to a, you'll get the opposite as if you integrate from a to b. 0. If you integrate from a to a, that is, you don't go anywhere on the x-axis, then the area under that curve from a to a is going to be 0. There's no area. You don't go anywhere, right? It's because the base length of the rectangle, the one rectangle that's there, is 0. So there's no area. That's pretty easy. That will become very important, by the way. Constant multiple. We learned this when we did the sine thing, but we reasoned it out. When we did that, remember that sine exploration we did? We were looking at all those different variations of the sine curve, knowing that the first one had an area of 2, and we tried to reconcile that. Do you remember what this integral was? If we went, it was from 0 to pi of 2 sine x. You remember what that result was? The amplitude was 2 on the sine curve. We stretched it up 2 like this. What did it do to the area? It doubled it because of this property right here. That 2 sitting right there can now be written out here. So the integral from 0 to pi of sine x is 2 times that multiplier. That's the k value. K value can just be migrated right out to the front. Anything that's multiplied by your function can be put right out here and dealt with later. Okay, that's another property. It's very useful. You'll see it used a lot. And that's what they're telling you in number 3. They're using a k, and then just down below it, they use a negative sign. If you've got a negative function and you don't want to deal with a negative, fine. Just pull it out front. And whatever you get, put a negative on it when you're done. Does that make sense? That -1 works just like any other constant coming out. Okay, the sum and difference one is very, very useful. If I want to integrate, dang it, I keep doing that. It's because I was just in algebra 2. If you want to integrate some function x, written in x like this, and you want to say add another function g, the dx on the back end of that, that's the same thing as the integral of f plus the integral of g. You can separate them out. In other words, if you're trying to do something like this, you're trying to integrate x squared plus 3x minus 2, what you're really doing, even though you wouldn't write this out, what you're really doing is this. You're integrating x squared, and then you're adding the integral of 3x. Do you see what I did there? Pull the 3 out. Minus 2 times the integral of dx. Pull the 2 out there. There's a dx on all these. You would integrate each of these separately. Though you would not write these out, you would just consider each of these individually and integrate them as though they were their own little problem. That's what we're saying. Okay? That's this property right here. And it wouldn't matter if you were adding or subtracting. It doesn't make any difference. This could be a subtractor. I want to talk to you, though, about this number 4 and how it will trip you up on the next quiz and on the next test and on the final exam if you do not get into this, what I'm about to tell you right now. This is true, what I just written up here. Whether you use plus or minus, it doesn't matter. If you have individual things added and subtracted, you can integrate them separately. However, I'll put this in red because this means stop. Don't do this. This is wrong. Don't oversimplify something like this. Sorry. That right there, that integral right there, is not this. You cannot take this plus minus property and just let it migrate into multiplication and division. That is not, well, you can hardly see that, the integral of f of x divided by the integral of g of x. It is not. The way you can remember that this cannot happen, if you hopefully you remember it, is that when we did derivatives of products, we had a product rule, which was much more convoluted and involved than just deriving this and multiplying. Do you remember? Yeah. Well, integrating is the opposite of deriving, if you haven't come up with that idea yet. Integrating, when we do that, is the opposite of deriving. So if you've got the integral of a product, you cannot just split these up any more than when you take the derivative of a product, you can just take the derivative of the individuals. You have to apply the product rule when you're deriving. You have to apply an entirely different strategy for products when you're integrating. Same with products, or same with quotients, because we have quotient rules for derivatives. You cannot simplify this to that. That's not the case. Don't sucker for it. It'll happen to you 3, 4, 5 times in the exercises. They'll try to make you sucker for it. We're going to try to get you on the quiz and the test too. Don't.
So what would you do in that situation? You time
I will not get to that yet. I'm just saying you cannot do it this way. This, as a matter of fact, this one and the composition of functions takes about an entire section in the book for each one. But you can't just simplify it the way you did these. If you'll recall, when we took derivatives of things that were added together, like if I wanted you to find the derivative of this function, you could derive each of these individually. Same with integration. But that's when it's plus or minus, not multiplication, division, or composition. So don't fall for it, okay? So they're giving you, on number 4, they're giving you the sum and the difference, but they don't bother to tell you in this list of rules what does not work. And what does not work is if you're multiplying 2 functions or dividing 2 functions. You cannot just do those individually. Okay, the next one is pretty easy once you understand how it's written. I want you to look at it with me on page 285. Bottom right there on number 5 where it says additivity. Look at what they're doing and look very carefully especially at the limits of integration. Notice that all the way through it, all three integrals there in this particular property, all are f of x dx, so we can ignore that, that doesn't change. But look at the limits of integration. The first one goes from a to b. That means the area under f from a to b. The next one starts at b and goes to c. Do you understand that that would be the same as the integral from a to c? It's just two different areas. One stops at b and the next one starts at b. That's a very, very useful thing too. You'll see all these things will be useful, but I just want you to understand that what's going on there is these limits of integration. A to B, for the first one, that ends at B, the next one starts at B and goes to C, which means you could just integrate from A to C and get the whole thing. They are the same. Okay, 6 and 7 are not quite so easy to understand, but once you see it, it's not too bad. Number 6 is called the max-min inequality. I'll just read it, and then I'll try to explain it to you. It says, if the maximum value of f and the minimum value of f are on the interval from a to b, well, whatever the max and mins are on the interval from a to b, we can be certain that the area under the curve from a to b will be trapped in between these two things. This is what it means. If you see it graphically, you begin to understand what the notation is trying to tell you. So if I have a curve like this, goes up this, maybe something like that, some function like this, and I want to integrate it from a to b, then what they mean by the min f means in this interval, the smallest y value that occurs is right here, isn't it, in this interval? So that this right here is min f. Okay? That's what they're calling it in that notation. This one right here, even though it came down a little bit over, this one right here is max f. And what they're trying to tell you is this. When you see it, when you finally see it graphically, you're going to go, oh, brother, that's a duh. But understanding the notation of what they're saying is pretty important. If I draw the rectangle that belongs to this distance from here to here and min f, I get this rectangle. Do you agree? And this rectangle's area, the green rectangle's area is b minus a times min f. That's its area. You buy that? Okay. If I draw another rectangle based on a height of max f, that would be this rectangle here, coming clear down to here, over to, oh, wow, that was pretty bad. Coming over to here, and then down here like this. Now, pretend this is down here. That's max f. Okay, so this rectangle, and I don't know how to actually show that because it also includes this right here, but I'm going to say the blue rectangle's area is going to be b minus a times max f. Do you agree? All right, so the actual area under the black curve is somewhere between the blue area and the green area. Makes good sense, right? Now that you see it, you're going, yeah, make your biggest possible rectangle, your smallest possible rectangle. The actual area under the black curve is somewhere in between those two numbers. That's all they're saying. It's just wild and crazy notation. See, they've got min f times b minus a. That's the area of the smallest rectangle you could draw associated with this function. Max f times b minus a is the area of the biggest rectangle, and the actual area under the curve, which we represented with an integral, somewhere in between. That reasonable? You understand what that's saying then? Notation's crazy, but once you understand it, see the picture, you go, oh, that's kind of stupid. The last one's called domination. It's pretty cool. It says on an interval from a to b, if the values of f are always bigger than the values of g, then surely the area under f is greater than the area under g. Does that make sense? That's kind of a duh too, right? So So if f of x is greater than 0, and that must be, we've got to have them all on top because we're not going to consider positive or negative areas here. So that very last statement there says, if f is always positive on the interval from a to b, then the area under f will always be positive. It's another version of domination. We good or not? Okay.
What's the blue g equals 0 therefore?
They're saying that it's a domination thing if the g function that we're considering, because we're considering f and g, if the g0 is 0. I mean, if the g function is 0. It's a very small version of that, but they're saying if g is 0, then this thing still applies this way. F is bigger than g. All right. Actually, before I explain that for you, what's going on since you're interested in it, is they're saying this domination thing for this is bigger than this one. They're saying that if the area under the it comes back to me all right now. They're just saying this thing where we use f and g applies it when we're looking at that and let g be 0 at that time, then this has to dominate this if it's all right. So look at example 1. People who write tests love this kind of question. And you will do several of these on your exercise. It's not very hard once you see it. They want to see if you understand those properties that we just discussed. So here's the deal. Here's the facts that we're going to run with. The integral of some function, the area under the curve of some function from x equals -1 to 1 is 5. If we go from +1 to 4, the area is -2, the net area. And if we go from -1 to 1 on a totally different function h, then the area under h from -1 to 1 is 7. Okay? So try to get that in your head and see if you can answer. What is the value of the integral of f of x from 4 to 1? 2, because they changed the limits of integration, the order of them, so we changed the sign on the answer. Does that make sense? That's the first property we discussed. What's the integral from -1 to 4 of f?
3.
Y'all see where the 3 came from? Because you guys were pretty quick with that. You're not just looking at the solution, are you?
No, I
You see what's going on? Because the first one started at -1 and ended at 1. The next one starts at 1 and ends at 4. So if we start at the first one and end at the last one, we would add those two areas together. Is that good? Okay. How about 2 times f of x plus 3 times h of x from -1 to 1?
31.
You think?
Yeah, 31.
Remember the property that says if you've got just a multiplier on the front of a function, you can take it out front? So what that means is twice the area under f plus 3 times the area under h from -1 to 1. That's 31. You write this with this guy?
Yep.
You good, Marissa? Okay, everybody okay so far? Okay, what is the integral from 0 to 1 of f? A lot of people with really rudimentary experience here and not really considering everything would say, oh, that must be 2.5. But that's only if f is symmetric between -1 and 1. We have no idea. So that one cannot be determined based on the information we were given. You can't just cut it in half because you're going to half the interval. That doesn't mean half the area. Okay. Next one says from -2 to 2 of h. Again, you're doubling the interval. Does not mean you double the area because we don't know what's going on in the function from -2 to -1 and from 1 to 2. We have no idea. Cannot be determined. So you can't make it. You can't extrapolate anything there. And the next one, -1 to 4 of f plus h. Doesn't mean you can just add them all together. Can't determine that one either. So think about the possibility of functions and don't allow yourself to generalize without grounds to do so. We okay on that example 1? Yes, no, maybe? Okay. Example 2 is really weird. It says, show that the value of the integral from 0 to 1 of the square root of 1 plus cosine x dx is less than 3/2. What? What is the biggest value that cosine can have?
One.
1. What is the smallest value that cosine can have?
0. No, -1.
-1.
That's true.
We're doing this, folks. When I ask you those two questions, we're doing it with this. Whatever the square root of 1 plus cosine x squared equals is this black thing. The biggest value, the max value that that function can have is when the cosine of x has a value of 1. Right? And so we know that the biggest value this can have from 0 to 1, because that, oh, and you were right about the cosine can have a -1. But only letting the x values be from 0 to 1 on this, and so we need to look, which is bigger, the cosine of 1 or the cosine of 0? Oh, no, we're not. Sorry. I do it wrong. The function that we're looking at, which is the square root of 1 plus cosine x, cannot have a value which is bigger than root 2. Yeah? It also cannot have a value which is less than 0. So what I'm saying is that the min f for this situation is 0 and the max f is root 2. And the actual area under the curve is somewhere between those two. What's the square root of 2? The square root of 2 is about 1.41, right? And that's the very, very, very most that this area could have from 0 to 1 is root 2. And that's about 1.41. And that number is less than 3/2. So you find the very, very maximum f. The a minus b is just 1 in this case because it's 1 minus 0. So we've got a 1 here and a max f of root 2. And the actual area under the curve is less than root 2, which is 1.41. So surely the area is less than 3/2. 1/2. Everybody clear on that? Pretty crazy. So what you got to ask, that's a max min analysis. Any questions so far?
Yeah, so if that was like 1 plus like 3 cosine x, then the amplitude would be a maximum of root 4 then, right?
Yeah.
Okay.
And so then we'd ask you to prove that it's less than 5/2 instead. Something like that. Okay. All right, so if you look on page, well, we're going to switch gears entirely here, so try to let your mind close that file and open a new one.
How we doing?
Good, how are you?
Good. I just said something around real quick.
We want to hear it.
Yeah, okay, good. 5th hour today, Mr. Richards is gone,
Okay,
so you can help me set up the gym
yeah, sure.
for tomorrow.
Oh, yeah, yeah. Okay.
Thank you.
Cool, thanks.
Okay, for a second.
Okay, we want to hear it. I know, we're going, what's he in for now? All right. So this average value of a function, if you understand conceptually what it means, it'll be far easier for you to remember how it works. The average value of a function, the author, I think, explains it in a rather cumbersome way, so I've got a better way. Okay. I'm going to explain it in this way, and I think this will help you remember it. I think it'll be more understandable too than the way he does it. He stumbles around a little bit with equations and definition of average and stuff like that. Here's the concept. You've got a function that looks something like this. Let's see if I can draw this right the first time. I'll go with that. Okay. And we're going to integrate from A to B. The average value of the function, meaning the average y value, and the values range from here to here. And I'm not doing max min again. I'm just saying that the values range from there to there. The average value is somewhere between here and here. And the average value is in a place such that if I do this, if I extend this A line up a little bit more and I draw this over here like this, if I claim that that's the average, I don't like that one. I gotta come down just a bit. Looks a little better if I take a little bit of time on this. Maybe here. If I claim that this is the average value, average f, for this function from A to B, only from A to B, what I'm saying is that this rectangle has the same area as the area under the curve from A to B if, and it's the average value, if this space right here that was lopped off has the same number value as, it wasn't lopped off, it was actually added in, as this, which was lopped off. If I take out whatever area this is, if I subtract that from the area under the curve and then add in this area, and these areas are the same, red equals blue, is what I'm saying. The red area equals the blue area. If the red area equals the blue area, then I have found the average value. I got to find a place between here and here that if I draw a line will add in as much area to above the curve as I lost below the curve. And if I find that, that's the average value of the curve. Pardon?
This seems like it'd be hard to find.
Oh, I'll show you what it is. To find that actual number on the y-axis such that this area equals this one. The amount that I'm adding in equals the amount that I lost in drawing the line. Then this must be true. The area from A to B of f of x must equal b minus a times the average value. The rectangle has to have the same area as the area under the curve if I find the right spot so that I add in as much area as I lopped off. It would have the same area. Do you agree? Or not? Yes, no? So this is the area of that rectangle that I found by drawing the line appropriately. This is the area under the curve, and they must be the same since I added on as much as I took off. Well then, the average value of f is 1 over b minus a times the integral from a to b of f of x. All I did is divide both sides by b minus a. Now, if you don't like the way this is written, then if it makes more sense to you, then you can write this like this. Nobody does, but you could. That's what I did to get from here to here is I divided by b minus a. Okay. If I put that over 1 and invert and multiply, then you get the one that I like. You see that? Oh, now my f is way down here. Okay. The author of the book, he does a whole bunch of, you can look at just above the f average 10 box. He does a lot of stuff with Newtonian notation and crap, and I've gone through it and it works. It's great, but it's clunky. I like this better. Okay, so the average value of a function, 1 over b minus a. They'll tell you what this is. So you find that fraction, and then you multiply it times the area under the curve. That's it. I'll give you the average value.
So it's just like a different way to find the area under the curve.
No, it's not. It's just saying if you to find the average value of the curve from here to here, sometimes that can be very useful, especially in a lot of story problems we're going to do. What is the average value of the function from day 3 to day 10? Okay. That can be a useful thing to know, and this is how you find it. Yes.
Is there a practical value for the average value other than just to find the area underneath?
No, I'm just using the area to show you conceptually what the average value means. The average value of the function just means the y value between here and here, that is the average of these all. If you could take all of these y values, this one and this one and this one and this one and this one, all those y values, see how this one's going to occur, they're going to kind of densify together, they're going to get dense right in here, and then they're going to spread out a little bit more quickly there. You know what I'm saying? That's the reason why f average is closer to this than this, because they stay flat here longer before we take off. That's the reason why it stays down. But all we're saying is if you could take all of the y values of this point and this one and this one and this one and this one and this one, add them all up and divide by how many we had, it would be this. And that's what the author uses to explain it. Is that average value means you add them all up and divide by how many there are, but there's an infinite number of them. So how the heck do you do that? This is more conceptual. The average value of the function is this y value. Between here and here, it's this y value, as long as we're on the function, this particular one from A to B. It's closer to the lower one than the upper one because this one stays down longer, it goes up. And knowing that actual y value, that's the average value of a function, can be very useful. And just have to trust me on that. This is how you find it if you want to find it. Okay. All right, so let's see if we can apply this. In example 3, it says, find the average value of 4 minus x squared on the interval from 0 to 3. Does f actually take on this value at some point in the given interval? What? We'll talk about that in a minute. Let's find the average value first. So f of x is 4 minus x squared. You have an idea in your mind what that looks like? On the interval from 0 to 3, is it, did they say? Okay, so there's the interval that we're going to go on, and we want to find the average value where a is 0 and b is 3. So to find the average value, we're going to type 1 over 3 minus 0 times the integral from 0 to 3 of this function. Now, I haven't given you the details on how to actually evaluate that derivative without a calculator. So evaluate it with a calculator. And take it, when you get it, divide it by 3. What is it? What is it? 1. This right here, when you evaluated it, was just 3. Divided by 3 is 1. So f average is 1. What does that mean? Well, let's take a look at the graph of this actual function and see what it means now that we have something that's not just made up. The graph of this function is an upturned or a turned over parabola, right? Because of the negative. And it's up here at 4. That's its y-intercept because it went up 4. And so to graph this using a quick graph like I taught you, you go out 1, down 1, out 1, down 3. Mind you, right there. And we have to go out 1 and down 5. These there, so right there. Okay, so it's this graph that we're looking at, and it's from there to there, 1, 2, and 3. And we're claiming that the average value is that. The question is the area under this curve, does this feel like that area right there is equal to this area right here? Well, make a different color. This area here combined with this one. I feel like the black is about equal to the red.
Wait, why are they on different sides of the curve? Oh,
Because it's always between the curve and the x-axis. Does that feel about right?
No, it's good now.
Okay.
Oh, it's still feeling weird.
That average value of 1.
It feels like that average value that you count through looks like it should be the x-axis that they should.
Oh,
It's
This-
not.
this is x. This is the line.
Yeah,
Y equals 1. Y equals 1 because that's the average value.
Conceptually, it looks a little funky.
If you look at the drawing the author has, it's a little more clear. It's just to the left of the definition for this problem.
So you're telling me that little rectangle that makes, and like the yellow box equals the area under that curve? Oh, wait, no, because that's negative, huh? So that's that.
Negative or positive,
So that's a big one
accounted
minus
for is the area under that, yeah.
Okay, that makes sense.
We good on this or not really?
Oh, yeah, fine.
Okay. So, they repeat themselves over there. They call it the mean value theorem for definite intervals. It's the very same thing we just looked at. Average value, mean value, same thing, right? Call it the average value, the mean value. They'll ask it either way. Find the mean value of the function, find the average value of the function. It's the same thing. Now, exploration 1 is really cool. I love this exploration. There's a lot of them in here that are okay, but this one's great. This one's very surprising, what will happen. Exploration 1 says, this is a really strange question. I'm not sure why anybody would want to know this, but we're mathematicians, we're curious about everything, so we want to know. Okay. Suppose we have a circle of radius r centered at the origin, like you see to the left there. What we want to know is the average length of the chords that are perpendicular to the diameter from negative r to r. In other words, perpendicular to the x-axis. Average length of the chords. Remember what a chord is? You're seeing two of them right there. The red lines are chords of that circle. And those chords are perpendicular to the x-axis. Do you even know how to find the length of any one of them, given an x value? Do you have any idea how to find the length of it?
Still very simple. Oh, I know it's a circle.
I don't know.
We got to do some investigating here before we're ready to use the average value theorem that we just learned. So here's a circle of radius r, and this is just a representative chord right there. And I want to know how long it is. Any idea how to figure out how long that thing is?
I have a question.
Yeah.
How many chords are you splitting it up to? You could split it up into as many.
Too many to count.
Okay.
The average length of every single chord is what we're looking for. If we could take all infinite number of them, add up their lengths and divide by infinity, the same size infinity that we use to add them up, that would give us the average length of the chord. But we're certainly not going to do it that way. We're going to do it with an integral. We're going to do it with an average value. But we want to find the average of the length of the chord, which means we need to know how to find the length of any given chord. What's the equation of this circle?
The square root of r, r squared minus x squared.
Okay, that's the equation of the circle.
Is it plus minus?
It would be plus or minus to get the full circle. How long is this chord right here?
2 times r squared minus x squared.
The square root of it. Yeah, it's twice this length. Look, if you go out here this far from the origin, out here, this value right here is x, right? Just some x value. How long is it from here to here? It is this long, because that's the y value on that function. That's how far we have to, if we go out this far, x, and we go up this far on to arrive at the circle, we have gone up the y value that belongs to this x, which is this. So the chord length is twice that. Isn't it? Does that make sense to you or not?
R squared minus x squared.
Yes, yeah, now I can see why you're all looking at me funny. That's what I get for talking while I'm trying to write. Thank you for that. Now, does it make sense to you that that's what the length of any chord is? Any given chord? Well, guess what, folks? This thing is so powerful. It will add up all of these lengths. It's an accumulator. An integral is an accumulator. It will add up. That's what this does. It's the sum. It's the sum of all of these lengths from negative r to r. We'll add them all up. And then, if we want the average, this is what they all add up to. The average will be then 1 over r minus negative r. That will be the average length, because this is the sum of the lengths, and we divide it by how many, by according to what we just learned. The average is going to be 1 over b minus a times the sum of all those lengths. Are you with me or not? Now let's see what happens. This is really, really interesting. Okay, I'm going to take that 2 out, like we learned to do before. And so it's going to be 2 over 2r, which will be 1 over r times the integral from negative r to r of the square root of r squared minus x squared dx. Dx. What? Now, based on what you did yesterday, what is this? What is the area underneath the curve of the top half of the circle? That's what that's saying. It's the top half of a circle, radius r. What is its area?
1 higher square.
Actually, no. I was gonna say row. I didn't. John said that. I was like, yeah.
Is that right? 1/2 pi r squared?
Yes.
It's the top half of a circle of radius r.
How do you know that though?
Oh,
The area of a circle. Yep.
And then-
Yep.
Ah,
Yeah, my bad.
Everybody clear on why this expression is this, reduces to this? Because this
Yeah.
means the area under a circle from the left end of its, from a left radius to a right radius. We good? Okay, so I'm going to multiply that times 1/r. What is that?
1/2 YR.
Pi r over 2, isn't it? One of the r's will cancel. If I put the remaining r in the pi and multiply by 1/2, I get pi r over 2. And I don't know why you would want people always ask me, why is that useful? It may not be, but it's still an interesting curiosity. If you want to know the average length of the chords of any circle, and you know its radius, cut the radius in half and multiply by pi. Anytime you wanted to, because we did it in general there. It wasn't for any specific circle. That's the average length of a chord, and I think that's pretty cool to do.
Oh, no. Oh, yeah, actually.
Yes.
Wouldn't the average length of the chord just be like in between R and the origin? Wouldn't that just be the average length?
That may be where you draw it. But the actual length of it will be whatever the radius is. If the radius is 4, you cut it in half, that'd be 2. The average length of a chord would be 2 pi. If the radius is 20, it'll be 10 pi. The average length of a chord. Doesn't tell you where to draw it. It just says that's the average length.
Okay.
I think it's cool. Curiosity. You guys know, this is pretty cool. Okay, the last thing in this section. No, not quite. The next thing on page 288 through 289, the bottom top. If you're in a good mood and you're kind of excited about math, which I can see in most of your faces, you're not, then doing what I'm about to ask you to do may cause you to have an epiphany, and it may not. It did me. But I love math. I'm always excited about it. So, we're going to do it, and we're going to try to get an aha moment for you. And if it doesn't work out, then I will explain what the aha is, and then you will lose the opportunity to have an aha moment. What I want you to do is get a piece of paper, and either trace or sketch as well as you can the curve to the left of exploration 2 on 289.
Oh, actually, no.
If we don't want to.
There's not to drive it back when you're at the sign. Doesn't have to be perfect.
Doesn't have to be perfect. No, it just has to resemble this pretty close.
Is it rocket surgery, right?
You can trace it if you're worried about your drawing skills. I'm not worried about mine because I know it's bad. So,
It's like using math.
That hurt me personally.
I'm worried erasing.
Oh, wow, messed up.
I like her, didn't you?
you want an eraser, Kyle? A big one?
No, that's okay. I just always use my erasers to mark these spots, and then I ran out when I saw that.
So it's still under.
You're gonna need one of these if you're gonna have to correct it. You're gonna have to take a shot at it.
What are you gonna have?
You grab one.
I'm thinking.
Things are wrong.
I just get everything always.
Such a classic.
Okay, this next part is gonna seem too tedious for you to even do, but here's what, first of all, before we do that, first thing you need to do is find an X value between A and B, and do not look at your neighbors. Look at yourself, find an X value between A and B, put a mark on the X axis. And when you've done that, you are not allowed to change it.
Does it matter if it's positive or negative?
No, anywhere between A and B, put a value, just choose one. And put a mark on the axis where you chose it.
Do we assign it a value?
No,
Okay.
just choose it and put a dot on the X axis.
Okay, then I'll work with-
I choose this one. You don't you change yours. Mine is not any better than yours. It's just arbitrary. Okay, now it may look like it's smack in between A and B. As a matter of fact, I'll change mine a little bit so it doesn't look like that. I know, I said not to change it. Don't change yours. I don't want you to think that I chose it to be right smack in the middle between A and B. I'll move mine over. Okay, so in the first part of this, it says copy the graph of F onto your own paper, which you did. Choose any X greater than A in the interval from A to B and mark it on the X axis. So we are to there. Very good? Now, this is the part you're gonna hate. Do it anyway. You can't have the epiphany without doing the work. You may still not do one. I don't know. I gotta go find something that I can use to make my straight edges with. I don't like that ruler. Hang on. I never use these things, but it's got a nice straight edge on it, and I can hold it. So, anyway, this has nothing to do with it. This is my straight edge, just like your straight edge. Here's what I want you to do, and you will do better and do this quicker if you have a dull pencil. Here's what I want you to do. I want you to start at A, and I want you to draw a vertical line, and then go right next to it and draw another one, and keep drawing vertical lines until you have drawn your last vertical line at the X that you chose. Now, just so that you understand, I'm doing mine backwards, because if I do it this way, every time I scoot this over, it erases, it takes pieces of this out. So I'm going to do mine from here back so it doesn't erase it. You can do that too if you want, but I really would rather you go from A over to the X value.
Am I supposed to be counting? How many do they have to be together?
Enough to make it black.
Wow.
Good thing I put mine on the left side.
Do not change your X to make your work easier. Just get going. And I want you to move to the right. It'll be easier to understand if you have done yours from right or from left to right. I have to go the other direction to not erase my stuff. Sorry for those of you that are viewing this online. You might want to probably have already decided to fast forward through this.
Listen. Rachel, put yours. Where'd you put yours? No.
Did anybody put theirs after it goes negative?
No.
Besides me?
I did.
Okay. Did anybody go really, really, really close to B?
Ryan.
No.
Okay, now, even though yours all look pretty familiar, pretty similar, a lot of them, do you understand that every one of you chose a different X? They just made it close together. Okay, and do you understand the idea of integral being the area under curve, that this space that I've got right here, the way I wrote it, if I put an X right here, that for me or for yours or whatever would be the integral from A to X of f of X?
Yes.
That would be the stuff that I just painted by drawing little lines, okay? And that this is different for all of you. That area is going to be different for all of you because your X was different. That's the most important thing to understand here. The actual area that you painted is 100% totally dependent on the X that you chose, isn't it? Then this integral, this area, if you think of this as an area, this integral is a function of X, the X that you chose. Now, I'm going to do a little bit of changing here, and hopefully you will be able to understand after I explain. So I'm saying that this area is a function, and I'm calling it capital F to distinguish it from this, is a function of X, and that it's no longer this X. This X and this X are not the same. This X are all the X's used to generate the function, right? That X is not the same as this one. So I'm going to change these to a dummy variable. I'm going to call it T instead. Doesn't mean time. Forget the time. That's not what it means. It's just something other than X. I could have chosen anything. Could have chosen Q. But the reason I changed that is because this X that I just wrote up here is this X that I chose that determined the size of the area. So this area is a function of choosing this X, but this function was just what we drew it in between, and it's got to have a different variable than this because they're not the same. We okay on that?
Yeah.
All right, so let's see where we are in this. Your shaded region represents, and notice what he did. It's the integral from A to X of f of t. Why don't we write it the other way I just explained? It says compare your picture with others produced by your group. Notice how the integral depends on which X you chose in the interval from A to B. In the interval, or the area, this thing is a function of the X that you chose. And it's different for everybody depending on that X. That's what it's function. Now, it says recall the F prime, capital F prime, the one that I chose to use because it matches you, is the limit of delta F over delta X. Recall that F prime. So I'm using this function here, F prime of X is equivalent to the change in X. We used to call it dx, which these are big changes though because they're fat like your pencil. Delta X over delta F. Right? Delta, yeah. This F prime would be over that. In other words, we're saying dy dx. Nope, that's wrong. df dx. Gosh. Does this notation look familiar to you at all?
Yes.
Yeah.
That's how we define the derivatives, the change in over the change in?
Yeah.
Okay, so going back to derivatives for a minute. And it says as X gets smaller and smaller and smaller, represent delta F in your picture by drawing one delta F, by drawing one more vertical shading segment. I'm going to do that. You're not. Because you probably don't have a red pen. And if you do, you can do this with me if you want. But I'm going to draw, right here's X. I'm going to draw the very next one. And I'm going to make it different from the others. And I have increased the area now, right? And this new X right here, this was X. This X right here is X plus delta X. That's its new location. In other words, the width of this right here is delta X. The width of that next segment, the width of your pencil lead. if you were gonna draw another one. Okay, so here's delta x is the red one now, so that's that little teeny tiny space, the width of this marker. What is delta f? What's the change in f? Remember what f is? F is the area under the curve, right? Dang it. How much did the area change? By the ink laid down by this red one, whatever that area is how much it's changed, right? This is the change in the area, which is f. We'll finish this. Thought I could get done. Look, okay. We'll wrap this up on Monday. You have all the information you need, folks, to do this assignment, so get going now. Sorry, we didn't finish.